Now let's see some example. Consider that the random variable x is uniformly distributed in the interval a equal to 0 and b equal to 10. Use Markov's inequality to find an upper bound for this probability. We have that if x is uniform, the expected value of x is a plus b over 2. In this case, is going to be 10 over 2, that is 5. And the variance is b minus a squared over 12. In this case, this is going to be 10 squared over 12, right? Okay, now use Markov's inequality to find an upper bound for this probability. The probability that x is greater or equal than 9. Using Markov inequality, this is less or equal than the expected value of x over 9 in this case. And this expected value is 5 over 9, so this is approximately 0.55 sets. Now, what if we want to use the Chebyshev's inequality to find that upper bound? We have this hint. We have to compare to this probability because this is the form of this 5 is the expected value of x. So this is the form of the Chebyshev's inequality here. Okay, so to do that, we have that the probability that x is greater or equal than 9. If we subtract a 5 on both sides, this is the probability that x minus 5 is greater or equal than 9 minus 5, sorry. And this is the probability that x minus 5 is greater or equal than 4, right? So if we have this region here, we have 9, 10, we have 5, we have 1 and 0. We have that those x greater or equal than 9 is the same as if we subtract them to the expected value. In this case, is 5, because this is the expected value of x plus 4. So if this difference is greater or equal than 4, this is the same region. Okay, but this is less or equal than the probability that the absolute value of x minus 5 is greater or equal than 4. So we are considering also this other region. So this probability here, if we consider there are two regions on both sides, here and here, this is greater or equal than just this region. So this probability is less or equal. But now here we have the form of the Chebyshev's inequality, and we can use it. So this is less or equal than the variance of the random variable over c squared. C squared in this case is 4, so this is going over 4 squared. And the variance is 10 to the square over 12, this over 16. This is approximately, and this is actually 25 over 48. This is approximately 0.52. So this upper bound says that this probability should be less or equal than 0.52. Okay, what if we want to calculate the exact probability and see, and we compare these bounds to see how accurate they are? Okay, we can calculate that probability using geometry or using the geometric distribution. We have different options to do that. We have also done it in the past lessons. And the PMF should be a height of 1 over 10 because it's between 0 and 10. And we want to calculate the probability that x is greater or equal than 9. So we want this region. And this region is actually, this is going to be, the distance is 1 times 1 over 10. So this probability should be 0.1. Okay. And finally, let's see this example. Use Chebyshev's inequality to show that the probability that a random variable takes a value at least k standard deviation away from its mean is at most 1 over k squared. So this is, if we have the probability that a random variable takes a value at least k standard deviations away from its mean, it means if we take the difference between the random variable and expected value, this should be at least k times the standard deviation Using Chebyshev's inequality, this should be less or equal than the variance of the random variable over the square of the c value, that in this case is k times the standard deviation, so it's k squared times the standard deviation of x squared. But this standard deviation square is the variance, so we can cancel this out, and this is 1 over k squared. So this probability is at most 1 over k squared.